Hello! Welcome to the presentation on making a living. To understand how people make a living from an evolutionary perspective, answering some ultimate questions, we're going to be focusing on a set of theory called human behavioral ecology, and I'll explain what that means in a couple slides. So we've already talked about how behavior has fitness consequences. We've discussed cooperation like kin selection, why these ground squirrels will only make alarm calls when their kin are near. And we've also discussed reciprocal altruism and how you might acquire fitness benefits by trading favors with other individuals. We've also discussed some proximate mechanisms like a cheater detection psychology that helps individuals pick out favorable reciprocating partners. And we also talked about the example of an aversion to bad smells like the smell of dung. Humans find the smell of dung disgusting, but to a dung beetle, it's attractive, it smells like home. So we have this psychology that helps us behave in ways that increases our fitness or our survival and reproductive success. And we definitely know that how you make a living can affect whether you survive, how long you survive, and how much of your genetic information you contribute to future generations. So we've discussed, are you energy efficient, like this sloth? Are you getting a lot of bang for your buck? Cars with better gas mileage will drive further, so you might get more out of the energy that you're consuming. We also discussed, do you choose quality mates, like this peacock? Or I should say the peahen rather, since she's the one doing the choosing. And the survival and reproductive success of her chicks might depend on the types of the genetic quality of the mate that she's chosen. And finally, we've touched on this topic of costs and benefits. So the ground squirrel is weighing the costs and benefits of alarm calling. The cost is you might get predated upon. The benefit varies on whether kin are near, and you're able to increase your inclusive fitness by allowing your kin to escape. So being able to weigh the costs and benefits and make contingent decisions based on local circumstances, local ecology, your own quality, presence of kin, these can affect decisions like, should I alarm call or not? And animals with behavioral responses that increase their survival and reproductive success, we expect to contribute more to future generations, so we would term that behavior adaptive. We also would expect that those animals are products of their ancestors who made decisions in that way, and this is how we explain behavior from an evolutionary or an ultimate perspective. So let's talk specifically about what behavioral ecology means. And this means that you're studying animal behavior from an evolutionary perspective, but specifically in the context of local ecological pressures. So for the ground squirrels, are there kin around? For this bear, foraging in a berry patch, it might be, should I stay in the berry patch or should I move on? It depends on how many berries there are. Are there other berry patches? Are there other things to eat? How hungry are you? How much energy do you have? A lot of your own circumstances, as well as what the environment around you is like, can affect how you behave, or can affect what we expect the adaptive value of behavior to be. So when we study animal behavior, we look at the current fitness value. This can be observed. How energy efficient is this bear being when picking berries? If the outcome of the behavioral decisions, move on, stay put, and forage more, if this increases reproductive success, so you're getting more calories per unit time than alternate decisions, then we consider the behavior to be adaptive. And there's been a lot of work done on animals, studying animals from a behavioral ecological perspective. And so luckily for anthropologists, all we have to do is think about humans acting in the same context, making decisions about picking berries, what might be an energy efficient way to pick berries, how long should you stay put, how long before you should move on to the next berry bush. And so we call this human behavioral ecology. Basically, we take all of this theory that's been developed on animal decision making and applied to humans, because human behavior has adaptive consequences as well, and also was shaped over several generations, many generations of individuals making decisions, reacting to local ecologies, and having behavioral outcomes. So we're going to abbreviate human behavioral ecology as HBE because it's a long phrase. And so we consider HBE to discuss how individuals make flexible decisions within an adaptive context. So this is just looking back to what is the fitness value of the behavior and how are people going to make flexible decisions based on the environment. So we start off by thinking about what's a behavioral decision set, what are the options available to individuals, what's scarce, what's constrained, what is forcing you to make a decision, why do you have to choose one or the other, and what are the costs and benefits of each of those decisions. So this is fairly straightforward, and we'll go through and talk about some examples. So first, just a simple example here. Should I pick more berries at this bush, or should I move on? Now, the scarcity in this case is time. There's only so many hours of light in the day, so if you're spending your entire day picking berries, should you stay at one bush, or at a certain point, should you move on? There might be some costs, other things to do. So you're picking berries at this one particular bush. One option is to move to another bush. If you stay at your first bush and you pick all of the berries and you can continue to sit there for the rest of the day and you don't move, then you're losing out on all of those other berries that you might be picking. And this is what we call an opportunity cost. And of course the benefit is berries or calories. And the context here, we have to know something about the local environment. If there's only one berry bush and you're chained to it, then of course you're going to stay there picking those berries as long as you can. If there's another berry bush loaded with berries very close by, you're probably more likely to move on to that one fairly quickly. Are there other opportunities? Did your mate come along and request something of you, or your children needing some other care? So there might be other opportunities, but for the most part we're going to stick with very simple behavioral decisions for the point of this lecture and this course. So one thing that's very important is that we're talking about behavioral flexibility. So humans are primates and mammals. We have very flexible behavior, and human behavioral ecology doesn't say pick berries. It says think about the local ecology. How well are you going to do picking berries at this bush? Are there other bushes nearby? What might be a strategy that maximizes the amount of calories you get today? So we're talking about predispositions for responses to different situations, and these are very broad behaviors that we're talking about. So we're talking about something like maximizing calories within a patch. I've been discussing the example of berries, but it could be rabbits. It could be automobiles. There's some great data on how car thieves forage efficiently for cars to steal. So these are very, very broad decision-making behaviors that we're discussing. So let's talk about another example. Here we go. Should I have another child? This is a decision that a lot of people are faced with. So what are the costs and benefits of having another child? Benefits: more genetic contribution to the next generation. Costs: well, is there enough to go around? Can you continue feeding your current children? How likely is that child to survive? What are your current resources? What does the local ecology look like? Are there lots and lots of berry bushes loaded with tons of calories you can feed everybody? Or is it a drought year and you might not be able to sustain all of the offspring? We talked about one example previously of siblicide in egrets. So in very, very good years, the parents could raise 2 offspring, but in most years they could only raise 1, and the older sibling would usually peck its younger sibling to death. So what are the current resources in the environment? That's a very important question. So for most of human history, we have made a living by foraging for foods, hunting, gathering, collecting, and extracting resources. Calories are our source of energy. The more calories you have, the more things that you can do, the more babies you can have, the more pregnancies you can sustain, the more mates you can chase after. So we would expect that individuals who are good at extracting resources have more calories and more time. If you're very efficient at digging tubers, for example, you can have a lot more calories quicker, so you can go home, make lunch, and have the rest of the day to spend as you please. Maybe finding a mate, maybe caring for your children. So in this case, we look at behavior and think about it as adaptive in the current context, and also as a product of previous generations who have passed along that adaptive behavior because it increased their reproductive success. So one way we can study this formally is called optimal foraging theory. And this again was developed among the animal behavioral ecologists. And it's basically applying the microeconomics of decision making, but assuming the goal of the behavior is to maximize calories gained per unit time. Now, microeconomics is just the study of decisions. So this is the study of how animals and humans make decisions about how to spend their time, and we assume that the most successful are those that maximize the amount of calories they get per unit time. So in this sense, your feeding efficiency can be translated into reproductive success. You've got more calories, more time, you can do more things, have more babies, care for your children and more effectively. And we think about the fact that there are approximate mechanisms that lead to these efficient behavior, and these are products of natural selection. So if you go and pick berries, if you've ever done this, say you're in a long line of bushes, at some point you just kind of naturally feel like you want to move on. You look at the next bush, there's a lot more, they're easier to get. You don't stay at one bush and picking mechanically until every single ripe berry is gone. There's some sort of proximate mechanism that nudges you to move on at a certain point. And it's these mechanisms that produce the behavior that are the products of natural selection. So when individuals are making a living, there's many aspects to consider, and we can talk about all of these with the context of optimal foraging theory to kind of really mathematically weigh the costs and benefits. So you can think about where to go, which berry patch should you go to, how long should you stay there, how long should you stay at each bush or within each cluster of bushes, what should you pick? If you're in a berry patch and there's also rabbits and birds and other types of fruit, there is a choice of what you spend your time doing. Do you spend your time hunting birds? Do you spend your time picking fruit? Do you spend your time picking berries? So there's a choice of the type of prey that you're after. So in parentheses, these are the optimal foraging models that we can use to answer these questions and look at efficiency and behavior. We can also ask, who should you go with? How many people should you take with you? Might pick more berries more efficiently with more people, but maybe you don't want to share your secret berry patch with others. How far should you travel from home? I'm guessing you're not going to drive to Maine to pick blueberries. You're probably going to go pick huckleberries in eastern Washington or something like this. So what's the cost of getting to where you want to collect food? Where should you live? Where should you locate your settlement? And we're going to talk about this as an example, and we'll talk about group size and patch choice as well. So let's do an easy one first. Now we're going to do this graphically, but a lot of these decisions are considered mathematically. Not anything we're going to worry about now, but just so you're aware. So how many people should you take with you when you're going to, let's say, go hunting, for example? So we're going to put number of people on the x-axis. We're going to put calories per person on the y-axis. So with one person, you've gone out and you've hunted rabbit, and you've gotten, let's say, 100 calories. Now with two people, if we think back to our cooperation lecture, we can hunt a stag. Now hunting stag is difficult. So let's say you're likely to get one, but you have to share it with another person. Now because there's so much more meat on the stag, you're still exceeding the number of calories you've gotten by just hunting rabbit, because you're splitting a stag in two, and that's half a stag is more than a rabbit. With three people, you're much more likely to get a stag and much more likely to get a big stag. So you've gotten more meat, even though you have to share it around between three people. But once you have more than three people, because you have to share that meat with a fourth person, you're actually getting a smaller proportion of the carcass, and it goes down even more with 5. So if we want to maximize the calories that you are getting from participating in a hunt, it's pretty obvious that if you want to maximize your calories for a day of hunting, you want to bring 3 people with you, or have a party of 3 total. And this is pretty much what we see when we study hunters in real life. This is a fisherman who's a hunter of the sea, and he's caught a whale shark, and you can see someone else is pulling on the rope. It's not possible for him to catch this large packet of meat on his own. He needs a teammate to help him out. And when you look at fishing parties from, this is one particular village in Indonesia, and a human behavioral ecologist has studied fishing parties extensively, they pretty much spot on get the number of people in their sea hunting parties to go out and hunt. They hunt sharks, they hunt whales also, to maximize the number of calories per person. And now these guys have never heard of optimal foraging theory, outside of the researcher probably explaining it to them after the fact. But nevertheless, they do behave in a way that maximizes the number of calories per person for a hunting party. So let's talk about patch choice now, just for another example of how we use optimal foraging theory in human behavioral ecology to understand the evolution of human behavior. So how long should you spend picking berries at a particular patch? Now this example is going to have a special concept in it. So let's say after 10 minutes, you've picked enough berries for 50 calories. Okay. After 20 minutes, you have those original 50 calories and you've picked an additional 30 calories. So after 20 minutes, you've picked 80 calories of berries. After 30 minutes, you have your original 50, you have your next 10 minutes of 30, and in the last 10 minutes you have another 20 for a total of 100 calories. And this goes for after 40 minutes and after 50 minutes. And you can see here, when you've spent a long time picking berries off the same bush, every 10 minutes doesn't bring an equal increase in berries. Every 10 minutes means you're getting a smaller proportion of calories here. And for those interested, or if you've had a class in microeconomics, this is the marginal value theorem, the fact that your returns to your efforts of picking berries are marginally decreasing with each time step. If you haven't taken microeconomics or you're not interested, don't worry about it. So we have to think, though, if time was unlimited, of course you should spend 50 minutes in this berry patch because that's what's going to maximize your calories. But we have to think about what's going to increase your fitness the most, what are the costs and benefits, and what is the ecology like? So now let's imagine a different world where you have limited time and you have 2 patches that you can visit, so 2 different berry bushes. So here's patch 1 and patch 2. They're exactly identical. The longer you spend in the patch, the more calories you get, but your calories are marginally decreasing with each minute spent in the patch. So how long should you spend picking berries? Let's say you only have 20 minutes. If you spend the whole 20 minutes in patch 1, you will get 80 calories. If you spend 10 minutes in patch 1 and 10 minutes in patch 2, you'll get 100 calories. So we would imagine, in this case, the answer to the question, if your time is limited to 20 minutes, the behavior we'd expect to see is 10 minutes in patch 1 and then 10 minutes in patch 2. What if you have 40 minutes? What's going to maximize your returns now? Well, if you spend 40 minutes in patch 1, you'll get 110 calories. If you spend 10 minutes in patch 1 and 30 minutes in patch 2, you'll get 50 plus 100, so 150. If you spend 20 minutes in patch 1 and 20 minutes in patch 2, you'll get 80 calories plus 80 calories for 160. So we would expect you to spend 20 minutes in each patch. And behavioral ecologists have special mathematical ways of figuring out very quickly what the most efficient thing to do is. Let's ask one more question. What if you have 40 minutes, but it takes 10 minutes to walk between the patches? So now let's think about, okay, we can spend 40 minutes in patch 1, that's 110 calories. Or we can spend, let's say, 20 minutes in patch 1, plus 10 minutes of nothing, because you're walking to the next patch. So that's 30 minutes plus 10 minutes in patch 2, so that's 50. So 80 plus 50 is 130. So we would still expect you to move. And you can imagine if the patches, the further and further the patches get to be apart from one another, the further the berry bushes are, the more likely you would be just to stay in one or spend shorter amounts of time in each one. So this is just an example of how we can look at the rate that you're acquiring calories, the scarcity that you're facing, and the benefits, which is calories, and the costs, which is in this case travel time, how we would expect animals to spend their behavior. Now on the quiz I'm not going to ask you to solve an example of this, but I just want you to understand the general principle underlying how we can predict behavior. We in this case are just looking for the behavior that maximizes the calories per minute gained. So I wasn't going to include this, but I thought this would be a fun little example because I have some great archaeological data to talk about this. So let's discuss where you might choose a place to live. Some costs and benefits. How good is your current site? You need to consider this. How good are other sites? What does the ecology look like? What are your options? And we're going to use something called the ideal free distribution. Again, not necessary for you to memorize what this means, but if you're interested in this stuff, we do teach upper division classes on this, and we'll talk about this in more detail. Okay, so current site, you're in site 1, and we can see that as the number of people in the site increases, the suitability of the location decreases. More people, more crowding, less resources, more waste around, it just becomes more uncomfortable the more people that are living in your site. So let's say you find another site. Now it's not quite as good. You can see that one person living in the site has a lower suitability than one person living in site 1. But the ideal free distribution tells us that if you're free to distribute yourself in an ideal manner, at what point would we expect you to move from site 1 to site 2? And it's a very easy calculation to do. We just look at how good site 2 is for one person, and we see that it's just less than the suitability of site 1 with 3 people living in it. So the 4th person in site 1 we would expect to want to move because person number 4 in site 1 can increase the suitability of the location by moving. So we've got some cool data from the Channel Islands in California, just off the coast near Santa Barbara. We have an archaeological record going back about 13,000 years of continual settlement and occupation. So what the archaeologists did was they went around and they ranked the sites for suitability. And they gave them basically a score out of 4. So this is an example of a high-ranking site. You can see it's got some nice kelp forests off the coast there. It's got a great watershed, a nice beach. It's a good place to live in the Channel Islands. Lots of resources. A low-ranking site is here. No kelp. Oops. Looks like my computer is a little slow. Let's go back. Here we go. No kelp. Rocky shore, no beach, little water runoff, not a very good site, not very many resources there. So what the archaeologists did was they went around on the islands and ranked all of the sites. So here are the first ranked sites, the best ones, nice beaches, kelp, water, that kind of thing. Here are the second ranked sites, the third, the 4th, and then what they did was they went and looked at the villages and where the villages were located. So in the early Holocene, the first location was in one of the highest ranked sites. So the first people to get there had their choice of all of the sites and they chose the best. As time goes on, we see the middle Holocene. So as things are getting more crowded, population is increasing, we see people start to living in filling up mostly the first ranked sites. Time continues about 3,000 to 1,400. We see lower and lower ranked sites. And lower and lower. So this pretty much reflects the ideal free distribution. As people are spending time in their settlements, as settlements are getting more crowded, they'll move to the next best place. And on and on and on until you've got people living in really poor sites. So I just thought that was a neat example of how we can predict where people will live. And again, these predictions from optimal foraging theory used by human behavioral ecologists, they're generalities. Of course, people don't always follow these. You can see a lot of sites where people were living that aren't ranked on here. Oops, we'll just go through these quickly again. So you can see the settlement pattern. First, second, third, fourth. So the question now that a lot of students will ask me is, yeah, but people aren't going out and doing math when they do these things. And the answer is, of course not. You're not doing math when you pick berries. You don't show up at a berry patch. Well, maybe I would. And like measure the density on the berry bushes and, you know, plot out this, you know, perfect trajectory. No, people are not doing this math. Even though we use math to analyze the behaviors, it's just a tool to represent how the proximate mechanisms are expected to shape behavior. And this is really the next big thing in human behavioral ecology. We don't have a very good understanding of what these proximate mechanisms are. We can show that behavior is adaptive. This is, you can see on the right here, one of the graphical representations of the model of group size, and you can see how it, you know, roughly represents that bar chart that we discussed earlier. But as of right now, human behavioral ecologists just act as if people have these proximate mechanisms, and we're still trying to really understand what those are. And we'll talk about some next time when we discuss evolutionary psychology. I hope you enjoyed this lecture. Please contact me if you have any questions, and thanks for listening.